Hello, I'm Professor Von Schmohawk, and welcome to YU. So far we have seen that roots can be written either as a radical expression or as an exponential expression. In either case, when writing roots, we would like to represent their value in the simplest possible way. We have seen that roots can sometimes be integers. For instance, the square root of 81 is 9. It is obviously simpler to write the integer 9 than to write the square root of 81. However, most roots are irrational numbers. In this case, writing the root as a radical expression is probably simpler than writing a long sequence of digits. In fact, we would need an infinite sequence of digits to exactly represent an irrational root. Even so, it is often easier to comprehend the magnitude of a numerical value, especially when it is rounded off to some reasonable number of digits. Which form is considered simpler might depend upon its use. A farmer who needs to build a square pen to enclose 50 square feet of space would probably not use radical expressions to specify the dimensions. Numbers are a much simpler way to specify dimensions. On the other hand, an engineer or scientist might prefer the radical expression, since it is not only compact, but it represents the exact value of the root without any rounding error. But there is another way we can represent this radical expression, which is still exact, but maybe even easier to work with. Notice that we can factor the number under the radical sign as 25 times 2. Now, instead of using a radical sign, let's write this using exponents. We saw in the chapters on exponents that we can distribute the exponent outside the parentheses to each term within the parentheses. In other words, instead of taking the square root of the entire product, we can take the square root of each term separately. So the square root of 50 is equal to the square root of 25 times the square root of 2, or 5 times the square root of 2. So when we factor any quantity under a square root sign, we can take the square root of each factor separately. Then, any factors which are perfect squares can be written as the root itself, eliminating the radical sign. Let's try another example, simplifying the square root of 300. In other words, let's write this expression with the smallest possible number under the radical sign. We can factor 300 as 3 times 100. Then, each factor can be written separately under its own radical sign. Since the square root of 100 is 10, the square root of 300 can be written as 10 times the square root of 3. In this case, it was easy to see that the number under the square root sign was the product of 3 times the perfect square, 100. This allowed us to take the square root of 100 and bring it out from under the radical sign. But in many cases, it is not obvious if there are factors which are perfect squares. For instance, let's say we want to simplify the square root of 3,675. To find out if this number contains any perfect square factors, we can first factor the number into all its prime factors. Doing this, we get 3 times 5 times 5 times 7 times 7, or 3 times 5 squared times 7 squared. We can then bring the square roots of 5 squared and 7 squared out from under the radical sign and write the expression as 35 times the square root of 3. 35 times the square root of 3 may be easier to work with than the square root of 3,675. However, there is another advantage to writing a radical expression in this form. Let's say that we wanted to divide this square root by the square root of 300. Now this quotient does not look very easy to simplify. However, remember that the top number is 35 times the square root of 3. And, as we saw in the previous example, the square root of 300 is 10 times the square root of 3. So if we like, we can rewrite this quotient using these simplified roots. In this form, it is easy to see that the numerator and denominator have a common factor, the square root of 3. We can then eliminate this common factor, leaving us with 35/10 or 7/2. Sometimes the roots of expressions involving variables can be simplified. As a simple example, let's say the expression under the radical sign is x squared. The square root of x squared is obviously x. But remember that the radical sign implies the principal square root, which is always positive, and the value of the variable can be positive or negative. Therefore, when bringing a variable out from under a square root sign, we must force the result to be positive by writing the absolute value of the variable. This is true for square roots, fourth roots, or any even root. However, we do not have to take the absolute value for odd roots. This is because with odd roots, when the variable has a positive value, the result should be positive. And when the variable has a negative value, the result should be negative. Now that we know how to simplify roots of variables, let's use this technique to simplify radical expressions with numbers and variables. Factoring the number under the square root sign, we can collect groups of factors which can be written as perfect squares and bring the square roots out from under the radical sign. Since a square root is an even root, don't forget to take the absolute value of the variables x and y. Radical expressions can be simplified whenever factors of the expression under the radical sign can be grouped into perfect roots which can be brought out from the radical sign. For example, let's say we want to simplify the cube root of 72. Factoring 72, we see that 2 cubed is a factor. So this factor can be brought out from under the cube root. Since none of the remaining factors can be grouped into a perfect cube, they cannot be brought out. And we have 2 times the cube root of 9. On the other hand, let's simplify the square root of 72. Once again, factoring 72, we see that 2 squared and 3 squared are both factors. So these 2 factors can be brought out from under the square root, and we have 6 times the square root of 2. So the square root of 72 can be written as 6 times the square root of 2, and the cube root of 72 can be written as 2 times the cube root of 9. In both cases, we factored 72, and then grouped the factors into products which were perfect squares, or perfect cubes, and therefore could be brought out from under the cube root or square root radical signs. We have seen that although the roots of some numbers can be represented by integers, most roots cannot be represented by integers. In fact, they can't even be represented by rational numbers. In the next lecture, we will see how the concept of roots, starting with the discovery of square roots, forced the world to adopt a strange new kind of number called an irrational number.